Thank you for coming. So today's title is Introduction to Random Matrix Theory. Well, actually, I'm not an expert in this field of mathematics, so that's why I put the title Introduction here instead of just Random Matrix Theory. But anyhow, so I'm just going to explain some basic theories and applications of the random matrix theory, and if time permits, then I'll just show a brief ideas and arguments of basic theory. So, let's begin with the definition. Well, the random matrix is matrix-valued random variable. In other words, it's a matrix whose entries are random variable. So the definition will be more clear in the next slide. Well, so the brief history of this theory is, by Wishart, it was first considered as a part of statistics and in the data analysis. And it became famous after Wigner used this random matrix theory to consider a statistical model for heavy nuclei atoms. So, Wigner was a mathematical physicist who studied, extensively about these kind of things. And nowadays it is widely used, as you will see later. But in mathematics, the main interest lies on the first, eigenvalue distribution. So, if you have a matrix, and then it is very natural to consider the eigenvalues of the given matrix. And this eigenvalue distribution is governed by the Wigner semicircle law. And the second thing we consider is edge distribution. In other words, the distribution of the possibility or probabilities of the largest eigenvalue. And it is governed by Tracy-Widom distribution. And finally, the gap distribution, which means the average distance or the distribution of distances between eigenvalues. And it is governed by Dyson-Sine-Konner. So here is some concrete example. So which is called Gaussian Orthogonal ensemble. So let's just consider a lot of random variables, so Zij and Yi's. All of them are IID. Well, IID means identical, independent, distributed. So all of them are identical, yet they are independent with each other, and all of them are real valued. And this just means zero. So if you take the expectation or the mean, then it's just zero, and the variance is 1. And for y's, we'll just take the variance 2, because of some convention. And finally, all the moments are finite. So actually these two are just kind of technical conditions. The most important one is the mean zero. And we consider n by n matrix, and n will become infinity. N by n matrix with ijth element is the same as the jith element. So this is symmetric. And moreover, we're going to normalize by dividing it by square root of n. So we have two different types of elements. One is diagonal elements, and the other is off-diagonal elements. For the diagonal elements, we use this yi, so the variance is 2. And for the off-diagonal element, we use this zij, which is variance 1. And because this condition, it is always symmetric. And perhaps they could use the names like Gaussian symmetric ensemble instead of orthogonal ensemble, but I don't know why. But they just use this orthogonal ensemble for this case. Because of the same reason, later we're going to have Gaussian unitary ensemble instead of orthogonal, but in that case, the matrix is Hermitian. So, in addition, if Zij's and Yi's are Gaussian, then now we can have Gaussian orthogonal ensemble. So we call this Xn Gaussian orthogonal ensemble matrix. Okay, so the most amazing thing of this random matrix is, this kind of graph. So well, if you use MATLAB, then you can, well, do the simulation very easily. So if you just make 1,000 by 1,000 symmetric matrix, and each of them just satisfies this kind of condition, so well, all of them are distributed by according to the Gaussian distribution, and with variance 1 and mean 0. And if you plot all the eigenvalues, so well, this is a histogram of the eigenvalues. So if you plot all the eigenvalues, then you can, well, check like, well, between, well, some value and some value, well, the matrix has this many eigenvalues, and from, well, around 20, this has this many eigenvalues. And, well, because all the entries are mean 0, you can, well, easily expect that the eigenvalues will be around here, around 0 in average. But moreover, it's true, so that, well, after a certain number, you cannot have, you usually don't have any eigenvalues. Likewise here. Moreover, the number is like 60 something, and this 60 something is like this. If you have 1,000, and if you take the square root of it, then it's 30, or about 32, right? 31 point something. And this is not normalized, and normalized means that, well, we wanted to divide it by square root of n, but if you don't divide it, then, well, square root of 1,000 is 31 point something, and if you multiply it by 2, then this is about 63 or 64. This number is about 63 or 64, which means that if you consider the distribution of eigenvalues, then almost all of them is between -2 and +2. Moreover, the shape of the distribution is like semicircle. It's just half of the circle. So altogether, Wigner, who first proposed this kind of random matrix theory, proved that actually that is a semicircle. So, well, in the form of the theorem, it is as follows. If you have a Gaussian orthogonal ensemble, and if you have n eigenvalues of xn, like lambda 1n and lambda 2n, data than lambda nn, and, well, so lambda nn is the largest one. And we consider empirical measure. Empirical measure is just like the average of all the delta measures at the eigenvalues. And we also have the semicircle distribution. Actually, this is just a function, but if you consider it as a distribution, then you can have 1/2 pi, because the normalization, times square root of 4 minus x squared, and the characteristic function that x is less than 2. So this is just the semicircle function, and if you have this measure and this distribution, then this empirical measure will converge weakly in probability to sigma. In other words, if you have any bounded continuous function f, and if you take the inner product, or the, well, if you just do the integral and calculate the difference, then this cannot be bigger than epsilon when n becomes large.
What is the notation? CBR?
Oh, CB means the continuous and bounded on R. Yeah. So, well, if you normalize it and if you draw the distribution of the eigenvalues like we did before, like this, then, well, eventually it becomes like the semicircle. And there are 3 laws I explained, the distribution of eigenvalues, and the edge distribution, and the gap distribution. So the semicircle law just tells that this shape is semicircle. And the second one is the Tracy-Widom formula, which tells that the behavior of the largest value at this, well, around this edge. So that's why we call this edge distribution. And finally, the gap distribution means that if you have a point E, which is in between -2 and 2, and if you magnify it, or zoom it, and if you consider the difference or the space between lambda I and lambda I plus 1, then this has some characteristic. So this will be governed by sign kernel.
You failed to collect the chi.
Yeah.
-2.
Yeah, right.
What kind of chi? You failed to collect the
Characteristic function. So. Yeah.
Sorry.
Yeah. So, Yeah, again, the H distribution. So, as I told you, the largest eigenvalue is almost always 2. But if you want to study it more carefully, then you can say more than that. So, in general, the largest eigenvalue is 2 plus order of n3 minus 2/3. So of course, when n is large, this is just like 0, so you can get 2. But if you zoom it, then you can see the structure like n to the minus 2 over 3, minus 2/3. And you can actually consider the distribution of the largest eigenvalue by, well, this minus 2 multiplied by n to the 2/3. Now this is not the, well, this does not have any order of n, so you can get the distribution of this number. And if you consider this is less than t, then the distribution function that satisfies f2, well, the f2 is like this thing, and this qx is the solution of the pen level 2 equation. So I don't want to explain all the details of this pen level equation, but actually this pen level person was very interesting person. So he was a French mathematician at the beginning of the 20th century, and in the World War I, he became a prime minister of France. And after World War I, he again became a mathematician. So he studied about the general relativity, like about those things. And then some years later, he again became a prime minister of France. So when he was not a prime minister, he studied about the differential equation. And so he just considered the different types of equation, and he made a huge list of kind of equivalent classes of second order differential equations. And he made 50. And among 50, 44 were very well-known equations, and 6 were not known at the time. So he named pen level 1, pen level 2, pen level 3, and so on. So this is pen level 2.
AIOT asymptotic.
This is area function.
Area function.
Yeah. So if you consider the asymptotic of this solution, then it becomes the area function. And the third thing is the gap distribution and the Dyson sign kernel. And for this, we multiply all the eigenvalues by a factor of n. And if you do that, you can consider, well, actually, we consider a Hermitian random matrix case because the symmetric case has a different kernel instead of this, and that kernel is much more complicated. So the Hermitian case or the unitary case is the most well-known. And according to the Dyson sign kernel, if you consider the probability density P, alpha 1 and alpha 2, where alpha 1 is around E with this vector, and, well, you consider a small region or the small domain of alpha, and then you can consider lambda 1 is in this interval with I equals 1, so the alpha 1 and alpha 1 plus the alpha 1, and the alpha 2 is between E plus some number with alpha 2 instead of alpha 1, and like this. So you have a joint distribution that alpha 1 is in a specific interval, and alpha 2 is another specific interval, which is a little different from the first one, but still very close, because we have the same E here, and this n, well, this n is very small, n is very large. If you consider the joint distribution like this, then you will get 1 minus sine over this square. In particular, if you have two identical intervals for alpha 1 and alpha 2, then alpha 1 and alpha 2 are the same numbers, so you have 1 here. 1 minus 1 is again, well, 1 minus 1 is 0. So it means that if you have, well, if you consider the probability of having two eigenvalues very near each other, then it's 0. This kind of phenomenon is known to be a level repression, which means that, well, the level is like the energy level of the quantum mechanics. So because, well, in mathematical physics, just people consider these eigenvalues as different energy levels. And this says that if you have two eigenvalues, then they cannot be very close to each other. In the language of the energy, the two different energy levels are just different. They cannot be close to each other. So, well, these are just the introduction for the basic theories, and now the applications. And before we go to the application, I just want to show the Gaussian unitary ensemble, which was the Hermitian matrices. So if you have psi ij and eta ij, and all of them are IID again means that independent and identical Gaussian matrices. So mean 0 and variance 1. And well, in this case 1, and we had 2 before, so again, there's some reason, but I'm not going to explain it. Anyhow, if you have n by n matrix with this condition, so now we have Hermitian instead of just symmetric. And each entry of this matrix is complex number. So psi ij plus, well, I don't want to repeat I. That's why I put this square root of minus 1 instead of I. But anyhow, so square root of minus 1 eta ij divided by square root of 2. So the real part is a kind of Gaussian, and the imaginary part is again Gaussian for the off-diagonal element. For the diagonal element, we just have this real number psi ij because, otherwise it's not Hermitian. And we call this kind of matrix a Gaussian unitary ensemble matrix. Okay, so the first application, the number theory. So here, well, I know an unbelievable story about this zeros of Riemann zeta function in IAS near Princeton. There was a mathematician whose name was Montgomery, who was an expert in this field of the number theory of the zeta functions. In one of his talk, he showed a very new result at the time about the imaginary parts of zeros of zeta function. Of course, we need to assume this Riemann hypothesis. Otherwise, we don't know, but we may have something different from the 1f plus something. But anyhow, if we assume the Riemann hypothesis, then all the non-trivial zeros will be on this. The real equals 1/2, and plus the imaginary parts. If you order it and renormalize it like gamma j, well, instead of using the gamma j, the imaginary part of the zeros of the Riemann zeta function, if you consider gamma j times log gamma j over 2 pi, and if you consider the spacing or the joint distribution, something like we did here, then you can consider a joint distribution such that the difference, the gap between two normalized eigenvalues will be in some fixed interval a comma b. Then this is this. So in that lecture, Dyson wasn't there. After the lecture, there was a tea time, and Dyson met Montgomery, and Montgomery tried to explain his very new result about this zeros of the Riemann zeta function. Then suddenly Dyson stopped his talk and he went to the blackboard and wrote down this. So Montgomery, of course, was very shocked because, well, he thought it was very new result about the Riemann zeta function, and Dyson, who was a mathematical physicist, has nothing to do with this Riemann zeta function. But he knew the answer, so Montgomery asked, how could you know this? And the Dyson replied that, well, if the zeros of the Riemann zeta function behaves like the eigenvalues of the random matrix from the Gaussian unitary ensemble, then the answer must be this. So, well, now people prove some relations between the zeros of the Riemann zeta function and the eigenvalues of the random matrix. And there are, well, many good results, I know. The second application, which actually was the first application of the random matrix theory, is the scattering resonance. Well, it was first considered by Wigner himself. If you have a heavy nucleus like rhenium, it's heavy, and if you shot neutrons using a neutron beam, then it scatters. But sometimes, if the energy level of the neutron is not, well, some exact values, then it does not scatter, but it just goes through the heavy nucleus like this rhenium. But in some other specific energy level of neutron, almost all neutrons just scatter. So it just, well, go to a different ways. So people could experiment the scattering resonances, which are the specific energies where you can find scattering. In other words, most of the neutron is reflected in that certain energy level E. So if you draw the peaks like so, well, in that level, well, you can see a lot of scattering, or less, more, and well, higher, like this, all the peaks. And people wanted to calculate what numbers they are. And according to Wigner, the scattering resonances behave statistically like the eigenvalues of GOE matrix. That's why Wigner proved semicircle. So if you consider the energy levels of these peaks, then you can recover the semicircle statistically. Third example is from combinatorics. So consider we have a deck of n cards numbered by 1 through n, and we shuffle it. And when we have a pile of cards, we just put the first card. So, well, we can just follow this example. We have 7 cards, 1 through 7, and after shuffle, we can get 4, 2, 1, 7, 5, 6, and 3 in this order. And we put the first card just first, 4. And we compare the second card with this 4. And if 2 is less than 4, then we just put 2 on top of 4. We have 1 as a third card. And because 1 is less than 2, we put 1 here. Now we have 7, but 7 is not less than 1. So we make another pile here, 7. 5 is less than 7, but it is not less than 1. So we cannot put 5 on top of here, but we can put top of here. So we put 5 here. 6 cannot be on top of this pile or this pile, so we need to form another pile, 6. Later, well, finally, 3 cannot be here, but 3 can be here, so we put 3 here. So we have 3 different piles from these 7 numbers. Now, you can compare this with the length of the longest increasing subsequence. So the number of piles was 3, right? And if you consider the subsequences which are increasing, then you can think like, well, 2, 5, 6, or 1, 5, 6, or 4, 5, 6. Well, whatever increasing subsequence you have, the size must be less than or equal to 3. 3 is the largest one. And that 3 is the same as the number of pile here. So if you have this kind of thing, and if you consider the distribution of the number of piles with this kind of games, and if you consider all this Qn, so Qn is the length of the longest increased subsequence, or the Qn is the number of piles obtained from this pi. Pi is just a shuffle. Then we can consider the distribution of Qn. So Qn, well, we can consider the probability of having Qn less than or equal to n for all pi's in Sn. Sn is the symmetric group of size n. And well, this Qn is less than n divided by n factorial to make it into a probability. Then Qn behaves like the largest eigenvalue of GOE matrix, which can be described by the trace-Widom distribution. So if you calculate this probability distribution function, then it becomes this after some normalization. So it seems like in the nature, if you have some very complicated structure, but still you can find some order, and that, well, most of them just come from the eigenvalues of the random matrix. And actually we have three different types of distributions: the semicircle and the trace rhythm distribution for the largest eigenvalue, and finally there's a sign kernel for the gap distribution. But well, you can match one of them to the things like this. And well, the most amazing application comes from economics. So well, the title is The Statistical Properties of the City Transport in Cuernavaca in Mexico. So well, this is a real story. In the city, there is no organization for the city transport. Instead, each bus is the property of the driver. So the drivers just want to maximize their profits. No timetable. Without any interaction, well, if you can just do the statistics and you can say that the distribution probability distribution is like the Poisson distribution. But to maximize the profits, the bus drivers hire people who record arrival times of bus at significant places. So they have some spots, and they hire people and put them in the spots, and they record the timetables of the buses. And using that information, the bus drivers try to optimize the distance. Well, because if you have a longer distance from the preceding bus, then you can get more passengers in your bus, so the profit will be maximized. And well, there are two different ways. One is slowing down, or second way is speeding up. Well, the speeding up means that well, you can just speed up so that you can pass over the preceding bus. And that can be better in some cases. In either cases, we have something like level recursion because the buses don't want to stay near each other, right? Whenever you have this kind of phenomenon, you can model that phenomenon by using random matrix. So some people tried to find the statistics of the bus arrival time, and they used the random matrix, and it was successful. And well, the final thing is, well, I don't know. But anyhow, so the result is reliable bus service and happy passengers and larger profits for the drivers. In other words, it is much more efficient than using timetables. But of course, this does not come from the random matrix theory. So I just explained different types of applications, but there are so many more. So in number theory, well, people can consider ranks of elliptic curves. Well, of course, I don't know anything about the ranks of elliptic curves, but well, some literature says that the ranks of elliptic curves has something with the random matrix. And wireless channels, well, in the information theory, it is, I know that well, it is widely used because the noise in the information theory can be modeled by Gaussian random variable and so on. And well, in neuroscience, they use random matrix because to learning in neural networks. And in finance, some people use random matrix theory to find the model of portfolio selection. In materials engineering, and they use the random matrix theory to model the crystal growth. And a lot more. It is like this. So when I was in graduate school, my advisor opened the course of the random matrix theory. And of course, well, we were in math department, but actually in the class there were, I think it was 11 students in the class. And among 11 students, we could find 8 different departments. Well, I was the only one. So, the story is like this. Because we have so many different applications of the random matrix theory, so people just want to study random matrix theory. And, well, of course, the most useful thing, 3 things are the semicircle, sine kernel, and trace without formula distribution. So people just try to use 3 different laws of the eigenvalues of the random matrix and make a model, and as the result, they can use one of these 3. But of course, in the mathematics, people want to do more. For example, if you have the semicircle, so this is the semicircle we saw earlier. So we have Gaussian orthogonal ensemble matrix X1, and we have eigenvalues lambda 1 through lambda n, and empirical measure Ln, and the semicircle distribution like this. I said for GOE matrix this is true. But of course, this is not the optimal form of the theorem, but instead of GOE, you can do much more general cases. Like for GOE, this is true, but if you omit this G part, so for OE matrix, OE is just an orthogonal ensemble without any Gaussian condition, but with IID. So if you have IID, means 0, and if you have a little more conditions, then you can get the same thing. Likewise, if you have UE, then you can get the same thing. And well, the interesting thing is that you can consider SC, which is symplectic ensemble. So you do the same thing about the symmetric or Hermitian, but now you can use quaternion instead of using real numbers or complex numbers, and you can define a similar thing. And then, of course, you need to use 4 different Gaussians for here. So, well, 1 for the real part, and the second for the I part, and the third for the J part, and the fourth for the K part of the quaternion. But still, you can construct the same, similar thing. Then you can get either GSE when they are Gaussian, or just SE for general symplectic case. Anyhow, whenever they are IID, you can get semicircular. Well, but of course, we have 2 different things like trace-Witten formula, trace-Witten distribution, or the Dyson sine kernel, and form of them would change if you use OE or SC instead of if you use GOE or GSC instead of GUE. But still the same is true. And the Dyson sine kernel is true without G, but if you use some more condition. And sometimes, even if it's not IID, it is true. So that thing will appear later. So let's prove it. And I'm just going to explain the idea of the proof of this semicircle law, because if I prove all the details for this semicircle law, then it contains so much analysis, and that analysis perhaps is something you do not see from the slides. But anyhow, you can see how combinatorics can be used in mathematical physics for this analysis. So let's consider the theorem. We have this minus this. The key idea is to approximate f by using a polynomial. So, after some arguments, you can show that if you can prove this thing for x to the k, the polynomial or the monomial, instead of this f, then you can prove the whole thing. So now we have x to the k. If you have sigma, which is just the semicircle, and if you calculate this integral, then it can be easily calculated. When k is odd number, then this must be 0, because this is even if this is odd. If k k is even, like 2L, then this integral is C sub L, where the C sub L is the Catalan number.
So what is original definition of a Catalan number?
There are so many different.
That number appears in the study of Riemann-Zeta function.
Well, I don't know if whether it appears in the study of the Riemann-Zeta function, but so the Catalan, can you see it? The Catalan number is defined. Well, I know there are so many different ways of defining it, but anyhow, this is from j equals 0 to k minus 1 times cj and c k minus j. Is it right? Yeah. Or you can, well, there are so many different definitions of the Catalan number. You can use the number of trees, or you can use some, well, I don't know.
What is C0?
minus 1.
Oh, this is minus 1? Oh, yeah, right. Oh, no. Oh, yeah, right. C0 is 1. Yeah. So what is the closed form for this CK? Is it?
It is 1 over k plus 1.
1 over k plus 1. Is it?
2k choose.
Is it 2k choose k?
Yeah.
Okay, yeah. So when I was studying for the Olympiads, well, I knew that there was a very well-known problem like this 2k choose k is a multiple of k plus 1. And you could prove it by using this Catalan number, because this is always an integer. So anyhow, well, if you have this integral like sigma nxk, and you can expand it by using the partial integration by parts, and you can recover this for this integral. That's why you can prove that CL is the Catalan number. But anyway, so this is just a calculus. For this part, we just consider the expectation of this Ln x to the k. Then, well, we have 1 over n, because it has 1 over n here, and we have this delta. So this delta just gives this lambda I to the n, right? So if you have lambda I to the, well, it's not the power, so it's lambda in, the eigenvalue. And if you have this ln and xk, then this, well, delta function will just give this eigenvalue to the k, so this eigenvalue to the k, and you have summation. So, well, in the language of the linear algebra, this is just a trace of x sub n k, right? Because if you have the kth power of the eigenvalues, then if you sum it, then it's just the same as the trace of this thing. Okay, and then the trace of x to the k can be written as this. So it's like so for example, if you have x squared, then this is just a summation I and j, xij and xji. Right? So the trace only consider the diagonal elements, and for this element to be a diagonal element, this I and this I must be the same, and this j and this j must be the same, because the multiplication of the matrix. And you can generalize this argument for the x to the k instead of x squared, and you can do this I1, I2, I2, I3, ik, and I1. It must be I1 because it's a trace. Well, so let's just call this whole messy thing, this T. We're going to prove, well, this mk n converges to this mk. Then, well, after some arguments, we can prove this converges to this weakly. Okay, when this I1 through ik are given, we want to draw a graph using these numbers. So for example, when we have, for as I1 through ik, if we have 1, 2, 3, 2, 4, 2, and well, I omit this 1 because the I1 is always the same as this one. If we 1, 2, 3, 2, 4, 2, then we first make 4 vertices, 1, 2, 3, and 4. And then we make an edge joining 1 and 2. So because we have 1 and 2 in the first pair, so we draw a line from 1 to 2. And because we have 2, 3, we draw 2 to 3. And because we have 3, 2, and we draw 3, 2, 2, 4, 4, 2, and finally 2, 1. Okay, so we can always draw a graph like this. First of all, if we have, for example, if you have 3 lines between 1 and 2, or 1 line between 1 and 2, and if you take the expectation of the whole thing, then because all of them are IID, you can just separate that part like this. And this to the 2L minus 1, so the power of some odd numbers. But because this is Gaussian, means 0, whenever you have some odd number, the average is 0. So it will just disappear. This is very powerful because when you draw the graph like this, you are not allowed to have odd number of lines between any 2 vertices. In other words, you cannot have 1 edge between 2 vertices or 3 edges. So if K if K is odd, then you have no way of drawing graphs like this. So at least one pair of vertices should be connected by an odd number of edges. Then it just becomes 0. So we just proved the half of the claim that this is 0. N as the index here. For this even number parts, of course, this is the most probable form of the graphs because, it has 2 edges, and 2 edges here. But sometimes you may have 4 edges or 6 edges between a pair of vertices. And for that case, now we want to count the number of possibilities of having vertices. So if you have the graph from I1 to Ik, then it has at most k over 2 plus 1 vertices. Right? Because this, we have 6, k is 6 here. And because the structure is like this and all the edges like this, we have 1, 2, 3, and 4. So half plus 1. Of course, if you have 4 edges between 2 vertices, then the number of vertices must decrease. So this is the maximum case. But if you carefully count the factors n, then you can see something. So, I didn't write it here very carefully, but this xn has a normalization factor 1 over square root of n for each term. So whenever you have this xn, and xn, you have 1 over square root of n for each k. So in other words, you have n to the minus k over 2 as a factor. So when n becomes large, this will kill almost everything. The only exception comes from this case because we have k over 2 plus 1 vertices and we have n times n minus 1 times n minus r plus 1 different choice of labeling the vertices from 1 to n. So that means that, when you draw this type of graph, you can say 1, 2, 3, and 4, but you have like 2, 3, 4, and 5, or 3, 4, n, and n minus 1. Different type of, different cases. And you have n ways of labeling this first vertex, and n minus 1 ways of labeling the second vertex, and so on. So you have this vector. So we have something like n to the this number. So we have n to the minus k over 2, and we have n to the k over 2 and n. The final 1 over n vector is here, 1 over n. So altogether, we can say, first, when n becomes infinity, the contribution from this whose graph has less than k plus 1 vertices is missing. So whose graph has less than this number of vertices becomes 0. And second, when the number of vertices is exactly k over 2 plus 1, we have this different graphs, and the C r minus 1 is the number of different ways of the drawing the structure of that graph. And that is the Catalan number, thanks to the combinatorics. So, well, we have this vector and blah, 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 and some small terms, and the small terms are just small. And we have this, and well, as n goes to infinity, this will become just 1. We have this, and also we have the variance to the k over 2. This is just 1 because variance is 1. So final thing, C of k over 2. So when k is even, we have this equals this, which is this. So in this way, well, we prove that the original claim doesn't work. So the original claim of this converges to this, and this is the main idea of this proof of this semicircle law. Okay, so the final slide, which is the most important slide of all, is the universality. The universality means that, first, we can consider different classes from the symmetry of the random matrix. So the first one is, as I told, the orthogonal ensemble, which means that the real symmetric matrices. And the second one is unitary ensemble, which is complex case and the matrices are Hermitian. And the final thing is symplectic ensemble, which is quaternion. And, well, I don't know if you can call this Hermitian or something different, but anyhow, you can see the logic. So you can have different ensembles, and actually we have much more different types of random matrix. So well, I didn't write it here, but you can consider, for example, Wishart was the first one who considered the random matrix theory, the Wishart ensemble, which is the form of T star T. T is a random matrix, but T is not a square random matrix, so it's just like n by n matrix. But then T star times T is a square matrix, and this is always symmetric or Hermitian or whatever. But the problem of this type of matrix is that this does not have IID property, because we had IID property, but now this has much more different structure than IID case. But in any cases, we want to prove the laws of the distribution of the eigenvalues, the gap, the bulk, or the edge. So the gap is the sine kernel, but the gap can have different meanings. Like bulk is the sine kernel, but the edge means that you can do the same thing like the sine kernel, but instead of using the sine kernel, you can put two eigenvalues. So in this picture, we use sine kernel for this part, but this was true because this E is somewhere not near to 2 or minus 2. When this E is very close to 2 or negative 2, then the sine kernel should change, and the distribution of the gap distribution is something like, well, the trace rhythm, or something which can be derived from the trace rhythm formula. So this is what we call the gap distribution at the edge. So, well, the distribution of the eigenvalues exhibits universal behavior that is solely determined by the symmetric class of the ensemble. So this is the final goal of the random matrix theory for the mathematicians. So people want to just exclude all the conditions like Gaussian. Well, so the Gaussian is almost excluded, so we don't use Gaussian. People don't use Gaussian in the proof. Or, well, the symmetric class is important because it can change the formulas, but sometimes people want to just get rid of IID condition. And well, if you exclude, well, if you just get rid of conditions, then you still need some, like the decay of the moments of each random variables or some things. And Well, as far as I know, the condition for the fourth moment of the random matrix is very crucial right now. And well, so anyhow, so this final goal of this random matrix theory is called the universality conjecture. So which means that, so this is, well, people believe that this is the reason behind all the applications. So whenever you have the random matrix or the natural phenomenon, then it can be modeled by the eigenvalues of the random matrix. It's not because they just obey the Gaussian law or something like that, but it is because all the random matrices are almost, well, the same. Okay, so, well, I think, yeah, that's the end of my talk. Yeah, thanks for listening.